Going from a system to a matrix, and going from a matrix to a row-reduced matrix would find us our solutions, because then we could read off our matrix to find exactly what x was equal and what y was equal to. This step of reducing a matrix to a row-reduced echelon form can be accomplished through Gauss-Jordan elimination, and is a method that will work for systems of 2 equations, or systems of 3, or systems of any size we have to deal with. The key idea of Gauss-Jordan elimination is that certain operations don't change the solution of a system. Here we have our system 3x plus 5y equals 0 and negative x minus 2y equals 4. Using this graphical tool, we see that they intersect, or that the solution of the system is at x equals 20, y equals negative 12. Here, if I multiply every entry of the second blue line by 2 to get negative 2x minus 4y equals 8, my solution stays the same, 20 minus 12. If I combined these two equations, if I added the red and the purple to get x plus y equals 8, I get a new line, a black line, but the solution is still 20 minus 12. Again, if I add both of these together to get a new line, say negative x minus 3y equals 16, I get a new line, but the solution is still the same. Gauss-Jordan elimination is a process of either multiplying some row by some number or adding 2 rows together and replacing a row with that. It might introduce new lines if we thought of it graphically, but the point where those lines intersect is still the same. For this class, we will use technology to perform the steps of Gauss-Jordan elimination, and it will not be expected to know how to do Gauss-Jordan elimination by hand. But we will need to know how to create a matrix from a word problem, how to use technology to get a row-reduced echelon form, and how to interpret a row-reduced echelon form to answer the original question. A group of 33 people want to travel in cars that seat 4 people, cars that seat 5, and vans that seat 8. There are 6 people who will drive. We have 2 people that will drive vans. No vehicle will be driven with an empty seat. How many 4-seat cars, 5-seat cars, and vans will be used? First, let's assign variables. Let's use U for 4-seat cars, I for 5, and V for van, as our question asks us how many 4-seat cars, 5-seat cars, and vans should be taken out. Next, we need to construct some equations that represent what we know. Let's look back at the problem to see what we're told. We know that 33 people will travel, and that they'll travel in 4-seat cars, 5-seat cars, and 8-seat cars. So we know that 33 people will travel. Each 4-seat car will carry 4 people. Each 5-seat car will carry 5 people. And each van will carry 8 people. Let's look back at what we know. We know that 6 people will drive. This tells us that our drivers equals 6. And since each vehicle only has one driver, we can also say that 6 vehicles will be used. Lastly, are there any other equations that can be found? We're told that 2 will drive vans. Well, this tells us exactly that V equals 2. Here are augmented matrix. First, we can start with the coefficients. 4, 5, 8, 1, 1, 1, 0, 0, 2. Sorry, 0, 0, 1. And our augmented column, what the right-hand side equals, 33, 6, and 2. Using technology to row reduce this, we get the reduced matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, 3, 1, 2. If we recall that the columns, the variables that they represented, were the 4-seat vehicles, the 5-seat vehicles, and the vans, we can interpret this augmented system, augmented matrix, to get U equals 3, I equals 1, V equals 2, which means 3 4-seat cars, 1 5-seat car, and 2 vans.